Have you ever stopped to think about how that photo you just sent, the one with the cat, magically turns from a bunch of ones and zeros on your phone into an invisible radio wave flying through the air? It's pretty wild, right? Well, today we are pulling back the curtain and diving deep into the secret life of your data right inside the LTE physical layer. Okay, let's get into it. So here's our game plan. We're going to start with the amazing translator that speaks both digital and analog. Then we'll check out the grid system where all your data gets neatly organized. After that, we'll follow your data's journey from the tower to your phone and then back again. We'll see how your phone finds its way in all the noise, and we'll wrap it all up with a handy little cheat sheet of the stuff you absolutely need to know. All right, first things first. Let's meet the star of today's show, the physical layer, or as engineers call it, the PHY. This is the piece of the puzzle that does the heavy lifting, acting as the translator between two totally different worlds. And this image right here, this captures the whole challenge perfectly. On the left, you've got the clean, orderly, predictable world of digital bits, ones and zeros. On the right, you've got the messy, chaotic, unpredictable world of analog radio waves. The PHY layer's entire job is to somehow manage this incredible, almost magical transformation. The best way to think about it is like a super efficient digital mailroom. The layer above it, the MAC layer, is like the boss who decides what to send. It writes the letter. But the PHY layer, that's the mailroom clerk that figures out how to send it. It's in charge of generating the signal, getting the timing just right, setting the power level. Basically, it puts the letter in the right envelope, slaps on the right postage, and makes sure it gets on the mail truck at the exact right second. Okay, so before our mailroom can send anything, it needs a place to organize all the letters, right? It needs shelves and cubbies. And that brings us to the LTE resource grid. You can think of this as the grand canvas where all our data gets painted. The first dimension of our canvas is time. And in the world of LTE, time is, well, it's incredibly strict. Everything revolves around these 10-millisecond chunks, called radio frames. But the real heartbeat of the system is the 1-millisecond subframe. That 1-millisecond window is when the network decides who gets to talk and when. If you miss that deadline, your data just gets left behind. It's that critical. Now here's where it gets really cool. When we add the second dimension, frequency, we get this beautiful grid. This grid of time and frequency is the entire playground for LTE. Literally everything that happens, every single bit of your data, every control command is carefully placed somewhere on this grid. So how does the network actually give you your own little piece of this grid? It doesn't just hand out individual pixels. No, it deals in chunks. And the smallest chunk you can be assigned is something called a resource block, or RB. This is the basic currency of LTE. When the network needs to give you resources, it's handing you these blocks. Okay, we've got our canvas, we've got our currency. Now let's follow a piece of data on its very first adventure, the trip from the cell tower down to your phone. We call this the downlink. And right away, we smash into a huge engineering trade-off. See, for the downlink, the tower talking to you, the system uses a technology called OFDMA. It's fantastic. It's built for speed and can push a ton of data. The problem? It creates these big, spiky signals that are super power-hungry. That's fine for a cell tower that's plugged into the power grid, but it would absolutely destroy your phone's battery. So for the uplink, when your phone talks back, it uses a different, more power-efficient technology called SCFDMA. So let's follow the data through the downlink assembly line. First, it gets a little error-checking tag, kind of like a quality control stamp. Then, turbo coding adds some extra bits to make it more robust, so it can survive the noisy trip. Rate matching stretches or squishes the data so it fits perfectly into the resource blocks you were given. Then it's scrambled to avoid interference and modulated, which is where the simple ones and zeros get turned into more complex symbols that carry way more information. Layer mapping gets it ready for multiple antennas, and finally, the whole thing is used to generate the OFDM signal, the actual radio wave. Now, one of the most brilliant tricks in that whole process is MIMO, which stands for Multiple Input, Multiple Output. It is an absolutely genius idea. By using several antennas on both the tower and your phone, the system can send completely separate streams of data on the exact same frequency at the exact same time. It's like taking a two-lane highway and just stacking another two-lane highway right on top of it. You double your capacity without making the road any wider. All right, time to flip the script. We've seen how data gets to you, but what happens when you hit send? Let's follow the data on its journey back to the tower, the uplink path.
At first glance, the uplink assembly line looks pretty similar, doesn't it? You got your error checking, your coding, your modulation. But hang on, look closely. Right in the middle there, there's an extra step. DFT spreading. That, my friends, is the secret sauce. This one little block changes everything for your phone.
So what's the big deal with this DFT spreading? Well, it's a bit of mathematical wizardry that basically pre-processes the signal. It smooths out those big, power-hungry peaks before the final radio wave is even created. The result? A much calmer, less spiky signal. And that means your phone's power amplifier doesn't have to work nearly as hard, which is the key reason SC-FDMA is so amazing for your battery life. Okay, so our data is now zipping through the air. But it's not a clear sky out there. It's a sea of radio static and other signals. So how on earth does your phone find the right signal? And once it finds it, how does it make any sense of it?
So when you turn your phone on, it's basically waking up in a dark, noisy room. It's totally lost. The first thing it does is listen. It scans the airwaves, listening for two very special beacon signals, the primary and secondary synchronization signals, or PSS and SSS. The PSS gives it a basic heartbeat to get its timing, and the SSS tells it the exact frame timing and the ID of that specific cell tower. Together, they're the "you are here" map for your phone.
So once it's locked on, the phone has another problem. The radio channel, the air between you and the tower, is constantly changing. It's like a choppy ocean. To navigate this, the phone uses reference signals. Think of these as a series of lighthouses sprinkled all over that resource grid. Your phone knows exactly where these lighthouses should be and how bright they should be. By looking at how bent or dim their light is when it arrives, it can figure out what the weather is like on the channel and correctly decode your actual data.
Phew. Okay, we have covered a ton of ground. So let's take a second and boil all of this down into a quick and dirty cheat sheet. The key takeaways that will have you thinking like a real LTE engineer.
After all that, here are 3 key questions you can now totally nail. Number 1, why does your phone's uplink use SC-FDMA? Easy. To lower the signal's peak power and save battery life. Number 2, why do the most important control channels use a simple, sturdy modulation like QPSK? Because for mission-critical instructions, you choose reliability over raw speed every single time. And number 3, what's the difference between CRS and DMRS reference signals? Well, CRS are the big public lighthouses for everyone in the cell, while DMRS are like private, personal lighthouses sent just for you, which you need for fancy features like beamforming. You know, when you step back and look at the whole picture, the LTE physical layer is just this brilliant symphony of engineering trade-offs. It's a constant balancing act between speed and battery life, between reliability and raw throughput, between complexity and efficiency. And that really leaves us with a big question to chew on. As we push forward into 5G, 6G, and beyond, what new compromises and what incredible new solutions are going to define the wireless networks of tomorrow?